In this lecture, we're going to talk about factoring polynomials. Now, if you recall, polynomials were expressions that could be written as a finite sum or difference of terms, or monomials, we call them, that are in this form, ax to the n, where n here is a whole number. N is whole. And remember the set of whole numbers, these are 0, 1, 2, and so forth. So we're going to see how we can factor the polynomials. This is again just a review of factoring. We're not going to go too much in details of factoring. You can refer to any intermediate or elementary algebra textbook or references online to learn more about factoring, if beyond what I do in this lecture. Now, the word factor, just to clarify, anytime we have two or more numbers that multiply together, or variables, doesn't matter, we call these factors. So in this product that I'm showing, I have three factors. 2 is a factor, 3 is a factor, so is 5. And the product, of course, 30. So this is one way to write factors of 30. The key word here is multiplication. So when we talk about factors, we're talking about product of terms or items or numbers. Now, in order to factor polynomials, I have a bulleted list of possibilities, choices that we go through with every problem when we try to factor those. The very first step is to identify any common factors that there may be. So what do we talk about common factors here? Let's say I have 2 times 5 is 10 and 3 times 5 is 15. So 10 and 15, the common factor between 10 and 15 is 5. So that's what we're talking about here. Now, two numbers may have many factors in common. G, greatest, means the largest that we are interested in. The next step in factoring process is to identify whether we have what we call difference of two squares. The difference of two squares, that would be this one, the second bullet. If we can recognize the form of this difference, then we can apply the factored form of difference of two squares, a minus b, a plus b. Notice the factored form would be product of two binomials. Next, in our factoring process, we look at whether we have product of two, whether we have a trinomial, special form of a trinomial, which we call quadratic forms. There you go. Now I have broken that down into two parts, because if you notice the coefficient, the number in front of x squared in the first bullet is 1, whereas in the second bullet, it's a, stands for any number, any real number other than 0. The easier of the two, of course, is the one that has a 1 in front. In either case, both of these, when we factor, the factors would be product of two binomial factors. Next step in our factoring process is factor by grouping, and the sign of factor by grouping, what tells us whether the expression could be done by grouping, is that we have 4 terms in our expressions. And what happens with 4 terms, we create 2 groups of size 2, and then we proceed. I will illustrate every one of these with an example in a few minutes. Next, we have difference and sum of 2 cubes. Again, if you recognize sum or difference of cubes, then this would be the factored form for each of those. And finally, we have perfect square trinomials. These are trinomials, like this one, in certain format, as you can see, it's special format that you're seeing. Now, these perfect square trinomials, when factored, they become product of two binomials, repeated, if you will, binomials. So we can write, for instance, in the first case, we have x plus y, so we can write it as x plus y squared. Again, the reason they call it perfect squares, because if you can imagine a square of side, let's say x plus y by x plus y, then we have the area of that square, which is going to be x squared plus 2xy plus y squared. So in that sense, it is a perfect square. So let's take a look at some examples of this for each of these factoring skills. Let me make a few exercises up here, or examples. So in this first example, suppose the expression is 9m to the fourth plus m squared. So the common factors in this expression, clearly, there's only one common factor, m. 9 doesn't have a common factor with 1 other than 1. Again, when we factor, by the way, because everything could be written as product of itself and 1. So 1 is a trivial factor in every expression. So we want factors other than 1. So other than 1, m squared does not have a number, a coefficient near it, attached to it. Therefore, there's no common factor between 9 and 1 other than 1. But there is 2 common factors of m, so we can remove m, and therefore we're going to have 9m squared plus 1. Now when we factor the GCF in this case, m squared, you literally factor out of that term. So for instance, 9m fourth, which is product of m squared. When we take the GCF m squared here, it's like taking physically out that factor. It's no longer there. So we have 9m squared in parentheses as the first term of that binomial. Same thing with m squared. Now note in the case of m squared, when it's completely removed, there's nothing here, so we just have a blank, right? Therefore, we can place, because we can't have a blank in our expression, right? So if you think of m squared as 1m squared, now taking out the m squared, and that's where this 1 comes from. Okay, so just want to clarify that. You probably knew it, but it doesn't hurt to just recall some of these trivial facts of factoring. Okay, so there you have that one. Sometimes we could have GCFs that are binomials. So for instance, let's say I have 14m plus 1 cubed negative, let's make that even number, 28, and then I'm going to create another m plus 1 squared, and negative 7, let's make it 7, m plus 1. So in this case, first we look at the numbers. On the number side, 14 2 by 7, 28 4 by 7, and 7 is 7 by 1. So clearly there's this factor of 7 in common, which we're going to remove. Now on the variable side, we have m plus 1 cubed, m plus 1 squared, m plus 1. So each of those have an m plus 1, a binomial factor in common, which we're going to remove again. Okay, now let's see, once we do that, what's going to be left over from that sum. So the procedure is to divide the first term by the GCF. The 14 divided by 7 is 2, m plus 1 cubed divided by m plus 1, or you can think about m plus 1 cubed as 3 factors of the binomial m plus 1. We're removing 1, that leaves me with m plus 1 squared. 2 additional binomial factors remain. Negative, let me put it here. So no, actually I should be okay up here. I was thinking maybe I don't have enough space, but I think I do. So now removing 7 out of 28 as a product, that's 4 times 7, so the remaining number factor would be 4. This expression is made up of 2 factors of m plus 1, which we're removing 1 of them. So that means we're going to end up with 1 additional factor. And finally, from the last one, the last term is the GCF. So again, think of it as 1 times 7 times m plus 1, which 7 times m plus 1 is taken out, leaving us with simply a 1. So I'm just going to write down minus 1. And there we have the factored form of this expression. Okay, so both of these involve just factoring out a greatest common factor or simply a GCF. Next, let's take a look at factoring, for instance, difference of 2 squares. For difference of 2 squares, Suppose I have 4x squared minus 9. Now, in order to apply difference of two squares or use that method, we need to literally see the expression as something squared minus something squared. Now, 4x squared as a term squared, we can think of that as 2x quantity squared, right? Because you get 2 squared and then x squared, so that's 4 squared. And then x squared. Negative 9 in its squared form would be 3. 3 squared is 9. So now we can write this as, this would be the a, that would be our b. So the special product or factoring formula for that was a minus b, and then a plus b. And there you have it. Okay, so it's really that simple. Remember, the key is to recognize which form we have. The form is what dictates our action. How are we going to do this? Let's see what else we had after difference of two squares. Oh, product of, okay, we have a quadratic expression. So let's take a look at the example of quadratic expression. In this example, let's say I have the case where in front of x squared the coefficient is 1, the easier of the two quadratic expressions. And then I'm going to go negative 2x minus 15. Okay, now just to put this aside, let's say I'm just going to show you a couple of the product multiplying two binomials. Let's see what happens here when we multiply binomials. So clearly we can do the FOIL method, remember, which is really distributive property. That's all FOIL is. So you multiply first terms, outside terms, inside terms, and last terms, and hence the acronym FOIL. So xx, that will make it x squared. The outside terms multiply to negative 8. The inside terms multiply to 7x, and the last is 56. Okay, and then the next step is we're going to combine middle terms, like terms, so that will be x squared negative x minus 56. Now the reason I did this one, and let's do one more and then I'll generalize. Let's say I have x minus 2, x plus 10. Again, FOIL will give us x squared plus 10x negative 2x minus 20. And then we can combine like terms, we get 8x minus 20. The middle terms are like terms. Now let's make our general observation here about these two. So if I look at negative x, which means really negative 1x, that is when we add 7 minus 8, right? Or 7 minus 8 becomes negative 1. The product, 7 times negative 8 makes negative 56. So we can think about negative 56 as product of 7 times 8. Of course, negative and positive makes negative. So one of the numbers would be negative. Let's take a look at the second one. X minus 2x plus 10. And now look at the middle term. Again, coefficient 8. That's when we add 10 and negative 2 to get the 8. Now negative 20, that's when we multiply the same two numbers. So we're going to let this be a guide as to how we're going to factor this. Notice the left side of my examples are factored form of the right side, correct? Which is a quadratic expression. So let's do this. Let's set this up as product of two binomials. And next we're going to search for two numbers whose product is negative 15. Because the product's negative, one of the numbers should be negative, the other positive, correct? Because if they're both negative, they multiply to positive. If they're both positive, they multiply to positive. Now 15, one of my choices would be 15 times negative 1. So that would certainly do the product. But look at, if I add, and it's got to be the same two numbers, we can change like 10 and 5 in the middle of this, or negative 20 and 5. Same two numbers, when we multiply now, we got negative 15. When we add them, we get 14. Okay, so this isn't going to work because we want the middle term, right? We want the sum to be the coefficient on the middle term. Therefore, this is not going to be a good choice of the product. So let's try, for instance, we're going to go 15. 5 times 3 is 15. correct? Actually, let me switch these for a reason. I'm going to go 3 and 5 here. So clearly we have negative 3 times 5, negative 15. We pinned down the product. Now let's see, negative 3 plus 5 is 2. But we needed a negative 2. So that's not going to work either. However, the fact that 2 is simply off by a sign, namely a negative sign, that's just a signal that maybe I can tweak these numbers and turn this one into a 5, that into a 3. I maintain the same product, and now the sum is negative 2, and here's the factored form of this one. Okay, so that's how we can factor these. They're pretty easy because the two numbers, you can find them readily, easily. Multiply to negative 15, add to negative 2. Now, as the numbers grow bigger, of course, then you have more choices of factors, and that takes more time. But in our work, we are focusing on relatively small coefficients. Okay, let's take a look at another one. Let's say I have 2x squared plus 13x minus 18. So this time now, look, the coefficient on x squared is 2. So we have slightly more challenging version of the quadratic expression. Now the fact that 2x squared is the first term, I'm going to try 2x times x in our FOIL process. That's how we can get 2x squared. Now what we set up here earlier, the product must be negative 15 in the previous one, still holds with this example. The product has to be negative 18. So for instance, negative 2 times 9 would work, and negative 6 times 3, for example. So you have a few choices here. Now, the fact that, again, the middle term is positive here, the positive here, tells me that the bigger sum of in the OI, that OI combination, is positive. Therefore, I'm gonna take a stab at this one. I'm gonna go plus 6, negative 3. And let's see what happens here. So when we do FOIL, we get 2x squared. The O part is negative 6x. Ooh, plus 6x. I'm glad it worked out that way. So that's going to be simply 2x squared minus 18. So we didn't even get the middle term here, 13x. And notice how close these two numbers are together. We want them to be further apart, right? We don't want them to be so close, because how else I'm going to get 13. So I'm going to scrap 6 and 3 here. And I'm going to actually try 9. Let's see, 9 times 2 would work. That should be okay. Let's try 9 and 2. Let's see what happens here. And in this case, we're going to have, let's see, 2x squared, 4x, and 9x. Ooh, that's negative 4x and 9x. It's going to be 5x. That's interesting. So it looks like actually this quadratic expression may not be, and in fact it cannot be factorable, because again, when I do the OI combination here, I get negative 4 plus 9 is 5, doesn't equal 13. Okay, so looks like that's good. I made an example of a quadratic expression that is not factorable, so we're simply going to say this is not factorable. Not every polynomial is factorable, so this is an example of one that is not factorable. Now, a polynomial that is not factorable, it's labeled as a prime polynomial. Okay, and this one would be example of a prime polynomial, means not factorable. So let's actually take a look at something that would be factorable. Let's try another example, maybe a simpler one. Suppose I want to do, how about this one? Let's say I have 2x squared plus 3y. Let's make that negative 2. I think that should work. Okay, and when we set this up, And the way we're doing this, by the way, is called trial and error, or guess and check. So we just pick out a couple of different combination of numbers and see which one works. There's actually another process in doing this, but I don't want to spend too much time on this. So trial and error is just as good. This time the product's -2, so I'm going to go -2 times 1. Let's see if that would work. Again, first, outside, inside, and last. No, that would not work. So let's try, this one didn't work. Let's try another combination here. 2x minus 2 didn't work. Again, the factors of 2 are not that many, correct? And we're going to go this combination now. Let's go -1 plus 2. Again, the first term multiply to x squared. First and last multiply to 4x inside, -x outside, -2, and now we have 3x. So there you go. This one worked. Again, trial and error, so don't be disappointed or discouraged. If you try a combination, it doesn't work, simply scrap the work and do another one that would possibly work. And remember, not every quadratic expression is factorable. Now, let me make up another example. Here, I'm going to try to combine what we did earlier. So, for example, let's say I have x squared minus 6x plus 9. And then I'm going to go negative y to the 4th. Let's see how we're going to factor this one. The fact that the first trinomial is a quadratic expression, so we're going to factor this like earlier. I'm going to set this up as x minus 3 and x minus 3. The two numbers multiply to 9, add to 6. Perfect, that worked. Now I can write this as x minus 3 squared, negative y to the 4th. And now at this point, we can recognize difference of two squares. Remember, the general structure or construct for difference of two squares is this. So I can see the difference is what got my attention here. Therefore, we can write this as, now think of this as a, this one as your b, so I have some form of a squared minus b squared. Okay, and then based on that, I'm going to write the factored form is a minus b. So here is a minus b would be y squared, because I'm thinking y to the 4th is y squared squared, so my b is going to be y squared. So it's a minus b times a plus b. And there you have the factored form of this one. All right, and we can work out the grouping symbols. Well, x minus 3, there's no number outside of parentheses. We don't need parentheses. The reason I did it up here the way I did it, just so you can see a minus b, a plus b explicitly. So I'm just going to write this as x minus 3 minus y squared and x minus 3 plus y squared. That'll be the factored form. Now, how do we know this is correct factored form? You simply have to do distributive property. If you want to check any factoring problem, you have to multiply them out, the binomials, polynomials, whatever there might be, or the monomials, and to see that you get the original expression back. And there you have it. Now, by the way, sum of two squares, a squared plus b squared, if we recognize it, but this is not factorable. And I should point out, when we talk about factoring, by the way, we're talking about real factors, integer factors. Later in this course, in our college algebra course, we'll see that every quadratic expression is factorable. No matter what we make, who makes them, they will be factorable. It's just, for now, we're looking for integer factors that are real. We're not talking about imaginary or complex factors, or factors involving imaginary or complex numbers, or radicals. For example, just to give you an idea, suppose I have x squared plus 4. Okay, well, If I write this as x plus 2, x minus 2, that's difference of two squares. So notice the product is not 4, it's negative 4. So this isn't going to work. So in this case, maybe if we could allow for, I don't know, complex or imaginary numbers, then this will be factorable in fact. But again, this one, we're just going to say in this review for real numbers and integer factors or coefficients, we're just going to call this prime for now. Okay, so we'll make a note of that for now. Let's try another example. This next example, we're going to try to do a cube. So let's do x cubed plus 64. Now x cubed plus 64, again, I can recognize the cube form of these numbers. So 64 is 4 cubed. Once we recognize sum of two cubes, then we simply apply the formula we had earlier. Remember, our formula was a cubed plus b cubed is a plus b, a squared negative ab plus b squared. So I'm just going to apply this to our expression. So this is going to equal to, acting as a, we have x, acting as a b, it's 4, so it's a plus b. And then we have a squared negative ab plus b squared. B is 4, 4 squared 16, and there you have it. Now, because we use the formula for sum of two cubes, notice in here we do have a quadratic expression in our general form, and so does here. Now, these will not be factorable again using real numbers. So there's no need for us to say, well, will this be factorable? Again, at this point, we're just going to say, no, that's not factorable because it came from the formula that found the factored form. If it was factorable, you would have seen it in the formula on the right side. So we're done with that one. Let's try another example. This next example, suppose I have, let's make it more elaborate. Suppose I have 8 x to the 6 plus 125 y to the 9th power. Now again, the key is to recognize these in their cube form. So 8 would be 2 cubed, x to the 6 would be x squared, and then the expression cubed plus 125, that's 5 times 5 times 5. So that's 125. And then y to the 9th, that would be y cubed cubed. So again, we have sum of two cubes, and we can just apply the formula. We just did sum. Let's make this in minus. There you go. Let's do difference of two cubes. The only distinction here, instead of a plus, we have a minus. So in our factored form, the first binomial is minus, and the only adjustment we make here is the plus sign in the middle term. So those are the only adjustments to the formula. Therefore, this is going to be 2x squared negative 5y cubed times 2x squared squared. Okay, and let me make bracket here, square bracket. Negative the product of 2x squared times 5y cubed, and then plus 5y cubed squared. And then we can further simplify within the square brackets. So 2x squared squared, that's simply 4x4. 2 times 5 in the middle term, I'm working on this one. 2 times 5 is going to be 10, so that's going to be negative 10. Then we have x squared y cubed plus 5y cubed squared. That 5 squared is 25, y cubed squared is y sixth, and there you have it. So that's going to be the factored form. So we applied all our factoring methods. We apply them all except, let's see, the one that we haven't done yet was I believe factor by grouping, correct? So let's try maybe do a factor by grouping here. Okay, now to see an example of factor by grouping, let's say in this example, I want to do Let me make one up. How about m n? That'll be good. M and n go together. M n, I'm going to square on this one, plus 7m, and then 3n squared plus 21. Again, notice that we have 4 terms, so that's typically the sign or the signal or the hint or the clue as to using this method, factor by grouping. Now, when we have 4 terms, we're going to make 2 pairs, a group of size 2. There are 3 possible choices of pairings that we can do here. So for instance, I'm going to list one. I'm going to go mn squared plus 21 as a group. And then I'm going to go 7m plus 3n squared as another group. That's just a rewrite of the expression above it. Now the next step, when we factor by grouping, we use this method. We're hoping that there is a GCF here and there is a GCF here. And further, once we remove the GCFs outside, next step we're going to see a couple of binomial expressions that look the same. Okay, so clearly with the choice that I have right now, that's not going to happen. So we're just going to X this out. We don't like that pairing. Now let's take a look at another pair here. It's going to be mn squared plus 7m. I'm going to pair those together. In other words, just a natural pairing the way they appear. That would be another option. And over here, I'm yet going to do that third possibilities of mn squared. And I'm going to do it with 3n squared as a pair. And the remaining terms would be 7m plus 21, those as a pair. Now let's work each of these and see what happens. Remember, the hope is we have a GCF here and a GCF here. And we do indeed. The first binomial, the GCF for the first binomial is going to be m. So I'm going to factor m out, leaving me with n squared plus 7. The second one, I'm going to factor the 3 out, leaving me n squared plus 7. So remember, our hope is to get a GCF from the first group, GCF from the second group. And then once we do, we're hoping that we have the same binomial for the next step. Now this binomial becomes a new GCF for the next step. So this is going to be n squared plus 7. We're going to remove it. And then I have m plus 3, and there is the factored form. Remember, from the first expression, you remove n squared plus 7. All you have is m, and that's what we write here. And likewise, we do the same thing for the one next to it. Now, if we carry this other pairing, let's see what happens. The GCF in the first binomial is n squared. Remove that, and we're going to get m plus 3. The GCF of 7 and 21 in the next pair, next set of binomial, is going to be 7. That's going to make it m plus 3. And now again, we recognize the common binomial factor. So that's a good sign. And we're going to remove it. Once we take out m plus 3, all that remains from the first expression is n squared, and from the second would be 7. So we have actually factored this one, and if you look at the answer, the answers are exactly the same. The order of factors, by the way, don't matter because of associative and commutative property of multiplication. So we can actually write, for example, ABC as ACB, BCA, BAC. There are 6 ways to write that. Okay, you can go CAB, CBA also. So it doesn't matter. These are all the same. Therefore, what we have up here, both of these are the correct answers for us. All right, so there you have this one. So I believe I've done one of every one except the perfect square trinomials, if I recall. I haven't done that. So let me do a couple of examples of those. All right, let me do an example now of perfect square trinomials. So in this example, suppose we have 16 again, m squared I'm using m and n's and other things other than x, so you just realize that these variables, what we call them, you could use m and p, q, whatever. We usually use x's, and you're going to see me use x a lot later on. But for now, I just want to show that it really doesn't matter what the variables are themselves as the choice of variable. A, B, C would work as good as x, y, z. Okay, so for this one, now in order to have a perfect square trinomial, remember perfect square trinomial went like this: x squared plus 2xy plus y squared. And we were able to write this as x plus y squared. So the key is to see the first and the last one in their squared forms. So in other words, I can think of 16m squared as 4m quantity squared, negative 40mn, and 25n squared as 5n quantity squared. So there's my x squared, there's my y squared. And with those choices, hopefully, let me go, yeah, that's fine. I'm doing the minus, but I said it doesn't matter. There you go. Remember we had two of those. Plus y squared is x minus y squared. So I'm doing this one. All right. Now, the 40mn here, we can see that as product of 4m times 5n. That product is 4 times 5, 20, and then 2 times that. That's exactly what the middle term is. Again, recognition is the key, and once we recognize this, then we can simply rewrite it. So this is going to be 4m negative 5n quantity squared. And there you go. It's really that simple. Now, if this was a plus, so it doesn't matter whether it was plus or minus. Okay, now, and of course, you can always set them up as product of two binomial, go through trial and error. It's just recognizing the form. These forms sometimes save us time in reducing the number of guess and checks. All right, let's take a look at, let me do one more here. How about something like this one? Suppose I have 6x to the 4th negative 13x squared and negative 5. Now we will work with expressions like this later on. These are expressions that are said to be quadratic in form. Okay, quadratic in form. What we mean by that is if you let, for an example, if you let a new variable u represent x squared. Okay, now if I square both sides of this, I get u squared is x squared squared, which is x fourth. And then we can substitute for 6x fourth, u squared. Instead of x squared, I can put in a u, and that's what we mean by quadratic in form. Again, that means underneath the facade of what you see here, you can recognize a quadratic expression. This time I let the variable be u. So this is, some people call it factoring by substitution. Now the hope is I can factor this one, and let's go through our practice here. Again, the factors of 6, I can go 1, 6, 2, 3. No, let me go 2 and 3 here. 2u and 3u. Now factors of 5, because 5 is prime, I don't have many choices here, right, for factors of 5, so I'm just going to go 5 and 1. Negative 5 and 1. Now the OI combination, notice if you add 1 and negative 5, you get negative 4, not negative 13. But that's not what we want anyway. The reason, because the coefficient on the square is 6, not 1. The only time the sum of these two numbers would equal to the middle term is if the coefficient on x on the squared is 1. So let's see if we have the OI combination. O plus I combination has to be negative 13 here for us. Here's the O, here's the I. 2 minus 15 is negative 13. Checks. Perfect. So we managed to get this on our first try. Beautiful. So again, this is an example of factoring those that are quadratic in form. Now don't forget, we need to replace u with the variable x squared because the expression was in x, not in u. So we're going to give the answer also in terms of the original variable. And that would be the factored form of this expression. All right. So with factoring, a lot of what we do, it really is a practice. The more you practice, the better you clearly get with this. All right, let's take a look at, now I'm just going to make a bunch of examples and go through them. In everything I'm doing now, we just want to factor. Okay, so for this one, again, the best I can do is factor GCF. The common factor between 12 and 60 is 12. So that's going to be 12m, because 5 times 12 is 60. And there you have it. Now, by the way, if you look at 12, 3 times 4 is 12, and 4 times 15, right? 4 times 15 is 60. So the two numbers, 12 and 60, have also a 4 in common, and they have 2 in common, they have 4 in common, and so on. The largest factor they have in common is 12. That's why the word G, greatest common factor, comes into play. If I just factor a 2, look what happens. 6m plus 30. So it turns out that 6 and m still have a factor in common, right? So I can factor, I don't know, in this case is 6. M plus 6 times 5. So notice 2 times 6, 12. Eventually I get the factored form, but I'm going through more and more steps to do that. The advantage of recognizing the GCF immediately is that it reduces the number of steps it takes to factor the expression. And the reason we like factoring, there are a lot of reasons other than the aesthetics, the way it looks better that way to some. But then later on, when we try to solve equations, these polynomials will be set equal to a number, maybe 0. It's much easier to solve those problems, and not much easier, but really one of the only ways to solve an equation that is equal to 0 is by factoring them. So that's why factoring is a key skill for us. All right, so I want to mention that. And while I'm at it, let's make the distinction between GCF and LCM. Greatest common factor here. This is largest, and this is least, meaning smallest multiple. Okay, so if I look at 12 and 60, for example, we said the greatest common factor. Remember, factor means product. As product of two numbers, the greatest common factor is 12, because 12 times 1 is 12, and 12 times 5 is 60. So 12 is the largest common factor. Now, when we talk about common multiples, not to be multiple of a number. So for example, multiples of 2 means 2 times every natural number. So these are multiples of 2. See that? 2 times 3 is 6, 2 times 4, 8, and so on. Multiples of 3 are 3 by 1, 3 by 2, 3 by 3, and so on. Okay, so when we talk about greatest common multiple of 12 and 60 now, that means not the greatest, but the least common multiple. Let's take a look at 12, for example. 12 times 1 is 12. 12 times 2 is 24. 12 times 3, 36. 12 by 4, 48. And 12 times 5 is 60. And of course, somewhere down here, let's say 12 times 10 is 120, which is 60 times 2. So 120 is a multiple of 60. There you go, 60 times 2. Now, when we look at multiples of 60, 60 times 1 is 60, and 60 times 2 is 120, and so forth. And in this case, notice we have common multiple 60, common multiple 120, and so on. As the numbers grow, the common multiples get larger and larger. Theoretically, it will go to infinity, right? So, for instance, 120,000 would be a common multiple of 12, and also 120,000 is a multiple of 60. So we don't usually want the largest common multiple because there is no largest. It keeps going forever. We want the lowest, the least common multiple. Notice the least common multiple of 12 and 60 is 60. So the LCM is 60. However, the greatest common factor means now product of two numbers that become 12 and product of two numbers that become 60. The greatest what they have as a number in terms or form of a multiplication is going to be 12. So you see the distinction between LCM and GCF. That's important in our work. Okay, so let's see, we've done this one. Let's take a look at maybe on a factored by, let's try maybe grouping something. Let's try something where we have to group them. So I'm just going to go 6xy plus 9, let's go y, negative 10x, and make that 15. I think that should work. So let's try these now. And in this case now, let's group the way they are, the natural grouping, first two, last two. Factor out 6 and 9, the GCF is 3, they have y in common, so that's going to be 2x is what's left over of the factors for the first group. The second one is 3. You could redistribute right away to make sure that we factored this correctly, by the way. 10 and 5, the common factor is 5. Let's factor negative 5, so that will make it 2x plus 3. And we know this is a good grouping because we're able to get a common binomial factor. Let's remove the common binomial, and what's left over would be 3y minus 5. And there is the factored form of this one. Let's do another one. Let's try something like 6, I don't know, a. Let's go with a. We've gone with every variable but a so far. Let's make that 4. Okay, let's try to factor this one now. Because of 6a squared, I'm going to go 2a and 3a here. The product is positive, the middle term negative. So that tells me that the two numbers must be negative because their sum is negative, right? And the product's positive. Okay, for 4, I'm going to go 4 and 1. Let's see, 8 and 3, 11. Perfect. First guess worked. And there's a factored form of that one. It really is really like it's crapshoot. You just try it and see if it works. I got lucky in that one. Let's try x to the 4th minus 81. Okay, x to the 4th minus 81. Now this one, difference of two squares, right? So let's write the squares in this one. X 4th, that would be x squared. 81, let's go 9. 9 times 9 is 81. So there we have difference of two squares. A minus b. A plus b, and there we have that one. Now notice, by the way, we recognize sum of two squares here, right? X squared plus 3 squared, but we just mentioned earlier that sum of two squared for now is not factorable. And next to that on the left we have again difference of two squares, right? X squared, there it is, x squared minus 3 squared. So we recognize that as difference of two squares, and so we can factor it. A minus b, a plus b, in our general form that we talked earlier, and there's a factored form of this one. So we factor them again as much as we can. Let's see, how about, let's do one where I use substitution again. So let's try, how about this one? Suppose I want to do, again, let's go m to the fourth negative 2m squared minus 48. That should work. So how are we going to do this one? Again, I can go factoring right off the bat, or I can notice because the exponent is fourth, we can do substitution. Let me do this substitution. I'm going to let u be m squared. If I square both sides of that, I get u squared is m fourth. Now replace m fourth here by u squared. Negative 2m squared is u, and minus 48. All right, and now we can write the factored form as u minus 6 times 8 is 48, minus 8, u plus 6. 48 and the sum negative 2. Perfect. And then we replace u with m squared. So it's m squared minus 8 and m squared plus 6. Now we could have done that from the get-go, from start. We don't need to introduce that substitution. So for example, to get m fourth, I know I'm going to get m squared, that product would be m fourth. And again, two numbers multiplied to negative 48, I'm going to go negative 8 plus 6 like before. And the o and the I here would be 6m squared, negative 8m squared. And of course, that will be the negative 2m squared up here that we need. So the point again, we don't have to go through that additional substitution right in here, but some like to do that just so they can see the quadratic in the next step. But if you're comfortable with factoring, we can factor from the get-go, and we get, of course, the same results. Okay, and that should work that one out. Let's see what else. Now, how about, well, let's do something this one. What if I do, so I have x squared plus xy, negative 5x, negative 5y. So we have four terms, right? Factor by grouping, first two, last two. Factor the x, I get x plus y. Factor the negative 5, and I get x plus y. And from this, I have x plus y, the common GCF, remove it. And we have x minus 5, the x, this x goes here, the negative 5 goes here. And factoring is complete. What about, oh, one thing, let me go back to this one. M squared minus a. So the question might be, well, can I see that as difference of two squares? Because it certainly has the components of it, right? It has first one squared minus second one squared. Remember, at this point, we're looking at, for this number, we're looking at perfect square numbers. Like 4, 9, 16, 25, right? Perfect squares. Those are when you square your natural numbers. When you square, you get 1, 4, 9, 16, 25, and so forth. They call perfect square again because like 16, that's a square 4 by 4. In that sense, it's perfect. So if a number such as 8, which is not a perfect square, we can factor this also. And let me just show you, because we'll be doing this later on. In order to see the square form of 8, I can write it as the square root of 8 squared. Correct? And that's still 8. Now I can factor this one. So it's going to be a minus b, a plus b. So yes, there is a way to factor the non-perfect square digits or integers, but the result's going to be radical expression. And we'll just put that on hold for now. Most of the one we do are going to be perfect square integers. All right. Now, how about, like for example, how about this one, 144 x squared plus 64? In this one, again, we can recognize sum of two squares. 144, that's 12 x squared, and 64 is 8 squared. But remember, sum of two squares are prime, so we cannot use the factoring formula. We do, however, have a common GCF we can remove, right? 144. See, 144, again, we said that's product of 12 by 12. Let's go 3 by 4, 3 by 4. 64 is 4 by 4 by 4. So there's a common 4 here, common 4 here, another common 4 here, and a 4 here. So it looks like 16 is the GCF. I can remove the 16 here out of 144. And once we remove 16, I have 9 x squared. 9 times 16 is 144. And remove 16 out of 64, we have 4 remaining. And that's really the best we can do with this one. So again, the point being, we cannot factor sum of two squares at this point if we are looking for real factors. All right, and now just maybe a couple of more, and then we're going to wrap this one up. So in this next one, so what if I have something like this? Suppose I have 4x to negative 2 plus 8x to negative 4. Well, these are factorable too. Notice the exponent is negative on x, but that shouldn't cause any issues for us. So for in this case, we're going to, because we're working with negative exponents, so I'm going to factor x to negative 4 here. And I'll show you why in a moment. So in order to factor x to negative 4th, that's the GCF. Now you may say, well, x to negative 2, how did you get x negative 4? Or how am I going to do that for x negative 2, correct? Well, the way to do it is this. I want to build x to negative 2 from x to negative 2 to x negative 4. So there you go. If I multiply by x to negative 2, adding exponents will give me x to negative 4. But then because I multiply by this, I have to multiply by x squared. So the net effect here is like multiplying by 1. That's because x squared times x to negative 2 is going to be x2, 2 minus 2 is 0, and 1. X to 0 becomes 1. So I haven't really changed the expression. But see, this is how I create x to negative 4. And of course, next to that, 8x to negative 4 is there. Now I can remove x to negative 4 out of this work. And I have what's left over, x squared plus 2. Because you factor a 4 out of 8, you end up with a 2. So this is going to be the factored form of this expression. Okay, now if you were thinking of factoring x to negative 2, 4x negative 2 here, 8x negative 4 is like 8x to negative 2 times x negative 2, correct? So if you factor that 4x to negative 2, now you have 1 plus 2x to negative 2. And you see in here, you still have a negative exponent, which we have to work with. So it's best if we do it the way we did it. Thus, remember, anytime you want to factor negative powers, you factor the one which is largest in absolute value. Okay, so if I have x to negative 2, x negative 4, x negative 10, you want to factor x to negative 10. The largest exponent in absolute value is negative 10. All right. And we will be working with negative absolute value, with negative exponents later on. And I think for now that's about it. We're going to keep this to about an hour long. So hopefully this was a a great review of factoring for most of you. And with that, we are done with this lecture. Thank you for watching.